things in a certain way, you have to have measures that will allow a meta-analysis. It'll allow your study to be put with other studies of similar things and combined. So you have to have effect size measures in these things. They'll also allow you to compare one subject to another. You want to see if one subject has a bigger effect than another subject. So having these measures and their standard errors allows you to compare one subject to another. You can do a little analysis within the study comparing your subjects. Okay, that's about all I want to say about overlap measures. Yeah.
Can I ask a quick question? For simple minds like myself, if you go back to your log odds ratio scaled by the 0.6,
Yeah.
it's about -2, right? About the actual results that you have.
Oh, the actual results.
It's
Yeah.
about -2.
Oops.
Yeah.
Yeah.
Could you just put that statistic into an interpretive frame for me? Like, what does it mean? What does it tell me relative to your original data?
Okay. If I were to have distributions of the behavior under the baseline condition, and it were relatively normal, and under the treatment condition, and it were relatively normal, I'd expect those two distributions to be separated by about 2 standard deviations, which is a very large effect. That's what the plus or minus, just which is subtracted from which, but it's 2 standard deviations separates the 2 distributions, which is in most cases is considered a pretty large effect. Does that help?
Absolutely. Could I ask a follow-on just real quick?
Sure.
Under, how reasonable is it that a normal curve that underlies that distribution?
How reasonable is it? The problem with most single case research is that there are too few data points to tell. So the one I just showed you was 6 points in one phase, 7 points in another. Unless there was a huge outlier, I probably wouldn't be able to tell whether that was reasonable or not. If you think about it, who gives you 6 points and says, is this normal? It just, you could draw, there are certain plots you can draw. If they're a nice 45-degree line, it's normal. But usually people are applying that to 50, 100, 200 data points, not to 6 points. If there were a huge deviation from normality, maybe you could see it, but most data sets of size 6 or 7, I don't think you could tell. And that's going to be true for a lot of what you do in single case design. Rob said, well, you should have 5 to meet the standards, and 3, well, meets it with reservations. Statistically, to do anything with 3 is almost impossible, and to do something with 5 is difficult, unless it's a huge effect and not much variation within phases. If you had really good control of behavior and did 5 and 5, you could get a statistically significant result probably, but it's difficult to have that good a control over behavior. You really need more measures. This is like the minimum if you're very lucky and people behave exactly as you hope that they're going to behave.
Would you combine data points across similar phases?
Would you combine data points across similar phases? Like AB, the
2
2A
A's.
phases, the 2B phases? Now you have to see, like call them A and A prime and B and B prime for the 2 different kinds. Are A and A prime similar enough that you want to combine them? Are B and B prime similar enough that you want to combine them? You can't just go by non-significant difference between them because they're based on small samples too. But if you want to make that assumption, yeah, it would work better that way. Anything else on overlap, non-overlap? All right, now I'm going to go on to the slightly more complicated topic, but I'll skip most of the complications. I'll just, for the people who are research and stat people, I'll give hints of what's going to go on and let them ask me in the breaks and at lunch to go into the other details. So I'm going to talk about work that I have done for maybe the past 10 or 12 years. Mostly with Will Shadish, and a person who helped a lot was Eden Nagler, who is my student at the Graduate Center and did her dissertation on a lot of these. She found these examples, and I helped her analyze this data. So the goals we had for our project were to develop methods for analyzing the small n designs using modern stat methods, and compare the results to simpler methods, including the test you now know about, the intraocular traumatic test. And this third thing was a big part of what we did, solve mostly unanticipated technical problems. There are all kinds of technical problems, including finding data that looked like we could analyze them. And all kinds of. We thought this might be a one-year project, even though we got 3 years worth of funding to do it. We thought we'd drift through it for a couple of years, but no, it was a project that continued over 2 grants, 6 years, and still we never solved all the problems. It just means there's more things to do, more grant money to be gotten, I suppose. Something I would encourage all of you methodologists to do is to look into the funding for your research on this from IES. And then eventually, something we didn't get to do much of at all was to develop methods for combining the results across multiple studies, to do a real meta-analysis of combining person A's work with person B's work and so on. And what happened was, just to give you a brief background, Will Shadish and I were on a technical advisory group for the What Works Clearinghouse when they developed these standards. And there was an emphasis in that group on developing standards for group comparisons, especially with random assignment. And there was a feeling among some of the people in control in that group that they shouldn't do anything else. And when I went back and told my students about what I'd been doing, and there was a school psychology student who said, well, what about single case designs? We use them a lot in our field in school psych, and you're not even considering them. And I said, well, okay, that's maybe we should go back and do that. And I had some interest in that because before becoming a statistician, my academic training included some things on behavior modification, so I knew about the designs and knew that they were widely used and they could be good. So I talked to Will about it, and he had the same feelings, and we decided to pursue this through grants. And what I'm going to do is to try to take you through progressively complex designs and show you some of what we can do easily, some of what we can do with a little effort, and some of which we still can't do after all these years. Some other people who did this, Rob kind of hid his statistical knowledge there. He was involved in one of these studies, one of the first studies that used multi-level models to analyze data from behavioral research. So Janet Marcus and Rob and some other people did a study of a meta-analysis of positive behavior support back in 2000. That was before the rest of us got on. And then some people from Belgium and got into this. Van de Noordgate and Angena combining, did a couple of articles. And I'm going to try to describe what multi-level models are about for people who don't know any statistics. All right, so here we go. What does the pattern of data look like for each person? And how can you describe it simply? Right? It may be as simple as baseline phase, they average 10, and treatment phase, they average 6 or something. And they're flat lines during each phase. Maybe that's as simple as it is. So what is the pattern? And so that's one person. What does the pattern look like for the next person? For the next person, so that's presuming you got several people in the design. So what does the pattern look like? How similar are the patterns for the different individuals? So what's the average pattern, for example? And how different are they? Do some people start higher, start lower, change more, change less? And then if there's variation, if the people don't all change in the same way or the same amount, what's responsible for that variation? How much of it can be accounted for by the characteristics of the individuals or the treatment characteristics? So that's conceptually what we're trying to do. We're trying to model the pattern of individual behavior for each individual and see what's in common across the people, what's different across the people, and how much of the differences can be explained by other characteristics of them, or if the treatment was done differently for some of them. So, if you're a statistician, you recognize there are some advantages to this, that it appropriately considers observations as nested within subjects. If you saw that I emphasized the word pattern, I didn't say anything about how many times each person was measured or what the exact timing was of that. So it means different people can have different numbers of observations or same or different spacing of the observations over time. If you think back to what you learned in statistics about repeated measures, the analysis of usual repeated measures, everybody's measured the same number of times. And everybody's timing is the same in those measures. For multi-level models, for HLM models, you don't need that. You can have people measured different numbers of times and different spacings of times. You're interested in the pattern. What pattern is their behavior falling into? Okay, it allows explanation of the variability across subjects. Now, first thing we ran into was a lot of you people just don't do what we statisticians want, right? You're just naughty. You know, we want these nice, normally distributed, dependent variables, and what do? You count things, right? You count things. That makes things more difficult. Now, I looked at a lot of studies, and you either get proportions of times something is done, or the counts, like the number of times somebody acts out or something like that. So it's a count of some type, some type either expressed as a proportion or as an actual count, or as a rate of behavior of something per minute or hour or whatever. That requires a different kind of analysis. So whenever you do that, you should do what you want. You should measure the right thing. But just remember, it's going to come back to bite you when you do the analysis, because it's a more complex analysis. Okay. Then I found sometimes change over time isn't linear. Impact is not instantaneous. You don't have an instantaneous effect. So you need some more complicated models for that, which I'll show you later on in an example. There's also a problem with all time series of carryover from one session to the next, which is called autocorrelation in statistics. So if you have that kind of carryover, you might have to account for it or take care of it in some way. And then you have these outliers, these data points that are all of a sudden a person does something entirely unexpected outside the range of usual. So all these things and more came up as problems as we were doing our analysis. So here's a list of the data sets that I used for some of these examples. So if you want, you can go back and see the details of what they were about.